Welcome to today's webinar. It's titled Scapulothoracic Rhythm Affects Glenohumeral Joint Force. And today we have an external speaker, which is Cesar Flores, who's a research associate at the Shiley Center for Orthopedic Research and Education. And I think together with Cesar is also his professor, Dr. Gerald de Lima. And Cesar is going to talk to us in a minute or so. But before we start, I'm just going to give a general introduction to the Anybody modeling system for those of you who don't know what musculoskeletal modeling is or what anybody is. So first things first, what is the Anybody modeling system? It's a simulation system for doing musculoskeletal simulations. It takes as input kinematics, that is motion data, and boundary forces, and then it simulates body loads, and that is joint moments, muscle forces, joint reaction forces. The Anybody modeling system is used in a wide variety of applications, from product design, economic analysis, things like surgical planning, outcome evaluation. You can also use it to calculate load cases for finite element analysis. And finally, Anybody is highly used in movement analysis and gait lamps. A typical workflow with the Anybody modeling system could look something like this. You would have the following inputs: motion data, and you will combine those with a body model and some sort of environment model that you build yourself, or maybe that comes from a CAD file. When you combine those things in the Anybody modeling system, you end up with a full model that you can run simulations on. And those simulations are what we call inverse dynamic muscle simulations. It calculates basically what the muscles are doing so that we can find the internal body loads, muscle forces, and joint forces. And those you can then output from the Anybody modeling system to do post-processing, for example, in finite element tools. And some users even close the loop completely to do design optimization, where they would change their environment. In this case, it's an exoskeleton, and then run this loop multiple times. Yeah, and with that, it brings me to today's webcast. So I will bring Cesar online. So Cesar, are you with me?
Yes, I am.
Thanks. So
hello,
Cesar,
everybody.
I will make you the presenter, and then basically you have the word.
I'm going to present a project that we did. We're located in La Jolla, California, near San Diego. We're a biomechanics lab. We're very interested in arthritis and shoulder joints, knee joints. And we did this project with the Anybody modeling system. And our interest was Scapula Motion and how it affects overall shoulder biomechanics. So what we found was that the Scapula Motion has a significant influence on the joint force, the force that the shoulder joint sees. We also found that increasing body height also increased joint. This is more intuitive because with height, the limb lengths increase and the external moments increase. We also found that increasing humeral head radius and the acromiohumeral interval decreased forces. So there were some findings, but the most important finding is that Scapula Motion, has a significant influence on glenohumeral joint force. So what is Scapula Motion? The shoulder joint is not just a single joint, it's several joints. And the most obvious one is the glenohumeral joint, the joint between the humerus and the scapula. But along with the glenohumeral joint, there's also a scapulothoracic joint. The scapula can also move on the surface of the thorax. It's very free. The scapula is basically floating on top of the thorax, and it can move in any manner of way. You know, it can elevate, it can rotate, and part of a person raising their arm is both the humerus rising relative to the scapula, but also the scapula rising relative to the thorax. So this is what we call the scapula-humeral rhythm. It's the ratio of humeral elevation with respect to scapular elevation. So the humerus will rise relative to the scapula, but also the scapula will rise relative to the thorax. And in a normal, healthy person, this is roughly a 2-to-1 ratio. So the humerus will elevate relative to the scapula 60 degrees to about 30 degrees of the scapula rising relative to the thorax. So when modeling, models, we're interested in modeling because we believe that they can help assess important measurements in terms of biomechanics. And for example, it's difficult to measure joint forces and muscle forces. So that's the whole point of modeling. So it's important to also measure the robustness of a model to uncertainties in the inputs and assumptions. But the question is, what are the important inputs? And that's what we set out to find out in this project. How important is scapular motion compared to other input variables when measuring, when modeling the shoulder joint? So this is called sensitivity. The goal of our study was to quantify the sensitivity of the shoulder model predictions to important model input parameters. So what we did was basically a sensitivity analysis using the antibody modeling system. So we had 5 input parameters: height, the height of the model, the body mass of the model, the humeral head radius, and the acromiohumeral interval, and the scapular motion. So we actually varied the degree to which the scapular motion moved compared to what the humerus was moving. So height and mass and even humeral head radius, they're more intuitively important parameters, and those have been accounted by previous models very well. But scapular motion is something that clinicians, doctors, orthopedists that deal with shoulder disease, they're very aware of it and actually use it as a clinical measure. You know, it's a diagnostic tool. You know, a scapulohumeral rhythm that deviates from what is considered healthy is a signal of disease, and it hasn't been as thoroughly investigated as some of the other parameters. So previous computational models like the Delft shoulder and elbow model, the scapular motion is prescribed. So it is accounted for. There is scapular motion, obviously, but it isn't varied. It isn't something that it's an input, but it's canned. It's something that is prescribed and not varied. So there hasn't been a commentary as to how varying that input, how will that affect the overall joint? How will that increase or decrease the joint force and the muscle force required to perform a given task. So scapulothoracic kinematics are an important component of shoulder kinematics. It's difficult to measure in vivo. We've seen other groups use fluoroscopy to measure the scapula motion. They've actually inserted pins into the scapula to track the motion. Non-invasive methods like motion tracking with surface markers or even palpation are not accurate, and they're not dynamic. It's difficult to use those methods in a dynamic situation. Like I said before, most models now, computer models of the shoulder now, prescribe the scapular motion as a function of glenohumeral motion. But these are assumptions, and they're based on healthy subjects. These are linear regressions of the scapular motion as a function of glenohumeral motion. But what we're saying is that the scapular motion is an independent variable that doesn't always correlate in some prescribed manner relative to the humeral motion. Scapular motion is highly variable, even in normal subjects. And fatigue, things like fatigue can even change it in the same person. And it's important because it determines moment arms and muscle lengths of muscles, important muscles around the shoulder joint. So we set out to analyze the relative importance of scapulohumeral rhythm using an any-body model compared to other more obvious shoulder input variables like humeral head radius and limb lengths, etc. So the way we went about this was using the any-body modeling system. We took the shoulder model that is found in the any-body managed model repository, which is based on the Dutch shoulder model. It's 7 segments: the thorax, the scapula, the humerus, clavicle, ulnar, radius, and hand. And there are 6 joints. The thorax is connected to ground rigidly. There's the sternoclavicular joint, so the clavicle is joined to the thorax with a spherical joint. And there's also an acromiohumeral joint of the acromion, the scapula, to the clavicle. And then obviously there's the glenohumeral joint, the humerus to the scapula, the elbow, and then there's also the scapulothoracic joint, the scapula joint to the thorax. We did make some modifications to the AMR shoulder model. We allowed for variation in scapular motion. By default, any-body scapulohumeral rhythm is based on the Gruden-Brand regression model, which is a relationship of the scapular motion to the humeral motion. But that's exactly the point of our project, to make the scapular motion an independent variable, independent from the humeral motion, and then to see how this affects, how important it is, how important this effect is compared to other input variables that most people have already investigated. We also changed the deltoid wrapping to allow for a varying humeral head radius. So as the humeral head radius increased, obviously the deltoid has to wrap around this larger head. So we built a base model. The base model was based on the average height and weight of a shoulder surgeon that collaborates with us. He has a large library of patients that he's operated on, and we know their heights and weights, so we were able to calculate a mean. And these are important variables because anybody then uses these two parameters to calculate the lengths of the limb and the masses of the limbs, which obviously affect the biomechanics of the model. We also had a scapulohumeral rhythm, and that was varied from a minimum of no scapular rotation. We had models that had no scapular rotation, so the entire arm elevation was all glenohumeral motion, and then we had a maximum of 1 to 2, so 1 degree of scapula of humeral elevation to 2 degrees of scapula elevation, which is a very extreme case. So we had models within that range, you know, any possible value in between those two ranges. We varied the radius of the humeral head from a minimum of 20 millimeters to 37 millimeters, and the acromiohumeral interval from 0 millimeters to 25 millimeters. And then our body height ranged from 1.4 meters to 2 meters. So these ranges, they're from the literature, and they're from means and standard deviations. But we chose to make uniform distributions for each of these parameters. So we had our base model, and then we varied each of these inputs within these ranges that I just mentioned. But the distribution of the values that we chose for these input parameters was uniform. So within these ranges, the distribution of the random values for each of these parameters was uniform, and that's kind of important. It's an important choice that we made. We wanted to investigate the effects of each parameter throughout as wide a range as is feasible, as could happen. But we didn't want to focus the data around the mean. So had we used a normal distribution, obviously the average model would be overrepresented. So what we really wanted to do was to investigate the range of each input parameter uniformly. So our simulation approach was the standard any-body model simulation. It's an inverse dynamics used to calculate joint reaction forces. So what the motion that we modeled was a person raising their arm, their extended straight arm, 90 degrees, and we have the model perform this, and then anybody calculates the muscle forces and the joint reaction forces. So what the whole point of our project was really to figure out how important each input parameter was, how much was the output that we chose, which was the joint force for the glenohumeral joint. How was that output affected by variations in each of the 5 inputs? So, and we chose the glenohumeral joint reaction force as kind of an overall, a single parameter that kind of described in a large sense the overall performance of the model. It's an important variable in terms of biomechanics, because obviously the force on the joint determines the stresses on the cartilage in the native joint, and the polyethylene in a joint that has been operated on, and it's also a good measure of the overall performance of the shoulder. So an overall outline of the sensitivity analysis to quantify the uncertainty in each input. So that's what we did. We picked the pertinent, the important ranges of each input, and then decided to use a uniform distribution, and then basically repeat the model. So make many different iterations of the model with different values for each of these inputs. In our case, we chose to do 1,000 models, and then we use the resulting model outputs to calculate the sensitivity of the output to each of the inputs. And that's kind of the power of Anybody. Anybody was just a great tool for this. We were able to build a virtual population of shoulders. We used the Python script to leverage the Anybody console application, and we're able to, in a straightforward manner, just build 1,000 different models with random values for the inputs within the ranges that we had chosen. Again, each parameter value was from a uniform distribution, and then each was varied independently of the other, so they were not correlated with each other. So that way we were able to quantify the interactions between different inputs. Here's an image of the Python script that we use to run Anybody. So here's an interesting image of the output, the joint force, for different. Obviously, this is not 1,000, which is the number that we chose, but you can see the different inputs lead to different outputs, and the wide variation of each of the models. So a little note on the computer performance. Our solution time for 1,000 Anybody models was about 10 hours on one of our desktop PCs. So it wasn't too bad. So the way we analyzed our data, we performed a linear regression. So we normalized the inputs and the outputs by the middle value, and basically assumed that the output was a linear function of the inputs, and then normalized. We solved the linear regression problem. We solved for each of the coefficients of this assumed linear function, and the resulting coefficients were the sensitivity of the output to each of the inputs. And we repeated this analysis for the output at 30 degrees, 40 degrees, 70 degrees, and 90 degrees of arm elevation. So for each level of arm elevation, we had an output, and we did this sensitivity analysis for each degree of arm elevation. This analysis assumes linearity, but this was valid because the overall R-square value for the analysis was well above 0.8, which is kind of the criterion that is accepted. So I'm going to share now the results of our simulation. We had an average peak force of around 400 newtons, and this figure shows the variation. So there's in black, there's the average, and then there's the distribution of the outputs. Interesting that although the inputs were from a uniform distribution, the outputs were actually normally distributed. So kind of to further explain this, you can see again here that joint force is a function of the inputs with varying sensitivities. So here we plotted the joint force with respect to height, and you can see that it's some linear function. And here we see that joint force is also a function of AHI with a different sensitivity, and the same for humeral head radius and for scapular motion. And this is for a single level of arm elevation. But then we can see that you can perform the same analysis for different levels of arm elevation. And as you change, this was also an interesting finding, as you change the arm elevation, the correlation of the output to each of the inputs changes. And here is the full sensitivity. So this is for every degree of joint elevation. So in the red is scapular motion, and you can see that it's quite, the correlation is pretty strong, but also that it varies with arm elevation, which was not entirely expected. Height remains an important input throughout. The acromiohumeral interval, it's interesting to see that it's not very important, but its important increases as the arm elevates to 90 degrees, which makes sense to us. The humeral head radius, interesting that it did not have as strong an impact as we expected it. So we compared the results, the joint force from our model to data from in vivo measurements. Bergman et al. has published joint forces, in vivo joint forces for abduction, shoulder abduction, which is the activity that our model was performing. And the joint forces predicted at 30, 60, and 90 were all within the ranges predicted for that Bergman measured. So you can see in red our predicted joint forces and juxtaposed with the data from Bergman. So it was interesting to see, to kind of get reminded again of the complexity of the shoulder, how the sensitivity of each input parameter. So it's not just that it's the sensitivity of the inputs of the output to each of the inputs changed with the level of elevation. So, and then the importance of the scapulohumeral rhythm, and how it can be disrupted during disease, and how important it is to restore it to this rhythm to a normal range is a major goal of rehabilitation after injury. So it was interesting to see how important it was relative to the other input parameters. So again, here's the kind of the take-home message, right? That the scapular motion is an input parameter throughout the range of motion, that it varies, it changes, the importance of the scapular motion changes as the arm rises, peaking around 60 degrees of elevation. We also see how height is always important. It's throughout the range of motion. It's an input parameter that really has an impact on the output, on the joint force. And then how the acromiohumeral interval width rises in importance as the arm reaches 90 degrees of elevation, but is inversely correlated to joint force. We chose linear regression just because of its simplicity, because it was justified given our data, the linearity in our data. We could have done one at a time. We could have varied each input parameter one at a time and found the correlation of the output to the input, but it doesn't account for the interaction between each of the input variables. Again, I remind you that although each of the input variables was varied randomly from a uniform distribution, the outputs were actually a normal distribution. So there was definitely some interaction between the inputs that performing a sensitivity analysis one variable at a time would not have accounted for. There's variance-based approaches, but this was not called for in our case because of the linearity that we saw in our system. We could have done a local method approach, taking a partial derivative of the output with respect to each of the inputs, but we were more interested in the overall, making a comment of the importance of each input parameter to the shoulder biomechanics, but taking kind of a larger view of the input throughout the range of motion, not near a certain value for each of the inputs. So we chose regression analysis because of the linearity of our data. We chose 5 input parameters because we felt those were the most important. I think height and weight and the radius of curvature of the humeral head and the acromiohumeral interval are pretty obvious choices for a shoulder model. The scapula motion also, to us, that we're very interested in the shoulder, seems like an obvious input parameter that should be investigated. But that was it because just due to computational expense limits, we did not want to increase the number of input parameters. Again, we chose the glenohumeral joint force because it's one output that kind of encapsulates the entire model. How much each of the overall muscle effort, and again, it's something that we're interested in anyway because we're interested in the stresses that are present in the joint. We chose 1,000 models, more arbitrarily, more or less. In retrospect, it may have been overkill. I think we could have gotten away with less, just given the R-square value and what the data looks like, the smooth regression coefficient curves versus elevation angle, and how narrow the 95th percentile confidence bands ended up being. So 1,000 was a good number, but I think we could have managed with less. So again, in conclusion, we found that increasing the body height increased glenohumeral joint forces, and this made sense because body height is correlated with limb length and the external moments of the weight of each of the segments. Increasing the scapula motion The ratio of scapular motion to humeral motion also increased glenohumeral joint force, and glenohumeral joint force is sensitive to scapular motion, which was kind of the big point of our project. We found that scapular humeral rhythm had a significant influence on glenohumeral joint force. The unexpected result that the scapular motion is not only important, but it also varies with shoulder elevation. This is a big message to shoulder models that we should pay more attention to the modeling of the scapula and its motion. It's not just something that can be prescribed. It varies with disease. It varies in individuals, and it has an impact in the large scale outputs of a shoulder model. Models of should we model scapular motion? Should we predict scapular motion? That would be fairly challenging, given the nature of the scapula, how it floats, how it's attached to the thorax via so many joints and so many muscles, how there are signals that are not strictly mechanical in nature, like pain and fatigue, that affect it, that change it. So this project is kind of a first page in the investigation of scapular motion. It's a first page in the sense that it just shows how important it is and how we need to pay more attention as to how we model it. I want to thank everybody for attending my presentation, and special thanks to my professor, Dr. Daryl De Lima, and thanks to anybody technology for all their support in making this project possible.
Thanks a lot, Cesar. That was really nice to hear. I think it's a nice project, and it really captures why we do modeling. Like, the human body is really, really complicated and nonlinear in many ways. Some of those things you can only really find if you model it. I think I'll just do an exit slide while people think about if there are any questions. You can write them, and then in a minute or so we'll do a questions and answers session. There are some questions that have come up, so we can take them afterwards. But this means that I'll just take the presenter role back, Cesar.
Okay.
For a little while, and then we'll talk again in a minute or so.
All right. Thank you, Morten.
Here at the end, I'm just going to say a few words. If you want to find out more about the Anybody Modeling System, if you want to read about events, dates, maybe see the publication list, you can go to the Anybody homepage, anybodytech.com, as you see here. I'll maybe point out that the publication list that you can find in there on the downloads is a really, really good resource if you do Anybody Modeling, because you can use that to find out who has published anything else within your field. So I recommend that. Other than that, you can go into our community page. It's called anyscript.org, and it has a lot of help resources if you're starting modeling. Then you can find a wiki site, and there is also a forum site which I want to highlight. And on this forum site, you can ask questions, and it's a really good place to get help from other Anybody users. Then finally, we have some upcoming events, or actually ongoing events, because if you are at the Vericon Europe conference on exoskeletons in Stuttgart, you can meet us there. One of my colleagues is in Stuttgart, so if you want to hook up with him and you are at Vericon, you can send us an email. The next webcast that we will have is probably going to be next year, I think. There might be one earlier, but it's not something we've planned yet. But we have one planned for the 9th of January on prediction of kinetic variables doing Parkinson gait. I think that's going to be a really interesting one from University of Miami. Yeah, other than that, I think I will look at the questions now, Cesar. So Unmuted you again. So there was like a few short questions that came in here at the end that we can maybe take first. Maybe one of them was from a person who didn't hear the beginning. So he's asking what was the population? I think I missed it. But that is fairly obvious. Maybe you can just it was a computational study.
So we had a population of 1,000. So we made a base model, and then for each of the 5 input variables, we chose a value for each from 1,000 different values from a uniform distribution.
Yeah.
So we kind of picked a height and a weight from a range that's reported either in the literature or one of the orthopedists that we work with. He's got a large population of patients, and we took that information from there. But
yeah,
the point is that we were able to make 1,000 models with different values of each of these five inputs.
So the attendee has a follow-up to that, is that like why then height and body mass? It's not something that you can usually vary or change in a single patient, but I guess your research question was broader than just the individual patient.
Yeah, so we can't change it in an individual patient, but you have patients that are that have a mass of 75 kilos, and you have patients that have a mass of 80 kilos. So there's a wide variation in people. So
yeah. So another question that came in: what was the challenges in modeling scapulothoracic motion? It's a very general.
So in our, I mean, obviously we have a model, right? But just modeling scapulothoracic motion is a challenge. In our sense, we actually prescribed it, right? Each of the 1,000 instances had a scapular motion that we prescribed. But if we were trying to, for example, solve for it, if we wanted a model that would predict scapular motion, it would be quite a challenge because there's so many muscles around the scapula. And like I said at the end of the presentations, the scapular motion is varied, is changed by the human body based on other signals that may or may not be entirely mechanical in nature, pain or stiffness, although probably stiffness of the joint would be easier to model
yeah. So also a few attendees are asking questions along the line of have you considered other motions like out of plane scapular motion, scapular adduction, tilt, these kind of things?
Yes, we did. So, but the scapula is kind of constrained. I mean, it does float, and it is constrained, but it is constrained to kind of, to a certain extent, to stay near the thorax. But the interesting thing is that the upward rotation of the scapula is the most important. So obviously it does move in it tilts in other directions and it slides. But when the arm is elevated, we found that the scapular upward rotation is the most important of all the scapular motions. It accounts.
Yeah, maybe I could also augment that, because like not all degrees of freedom of scapula are independent. So you cannot just rotate scapula around like doing scapular tilt without also moving other degrees of freedom. It's not like all 6 degrees of freedom of scapular is free. They're basically linked together, both in the model and in reality. So that's a good point. Another question is, can we use this approach for different pathologies like rotator cuff tears or shoulder arthritis?
Yeah, this is Daryl. And so one obvious approach would be, and we looked at actually taking out the rotator cuff. That means deleting it or inhibiting the muscle activity, which is what happens mechanically with rotator cuff disease. But one of the challenges we faced was the patient's biomechanics is also affected by pain. And we're not sure whether the abnormalities in scapulothoracic rhythm starts with pain initially and causes the abnormality, or whether it's the abnormality in the scapulothoracic rhythm that causes pain. And that's something that we are studying clinically first to get some validity for our assumptions. Shoulder arthritis is important, and as Cesar mentioned, the forces on the glenohumeral joint, we believe, at least in some extent, just like the knee joint or the hip joint, contribute to cartilage degeneration. And we find different patterns of shoulder arthritis. Some of them wear in the center of the glenoid, some of them, the glenoids wear out in the back, and all of these create different challenges for the surgeon during reconstruction. So we have to get into more patient-specific modeling to determine how the vector of the glenohumeral joint force, which then might be able to predict the type of arthritis the patient is at risk for. And then finally, which may be more feasible, is post-arthroplasty. So the treatment for end-stage shoulder arthritis is shoulder replacement. And we're still understanding the biomechanics of shoulder replacement. And surgeons are just using conventional wisdom or intuition in terms of designing and placing the joints, and how these affect the biomechanics of the complex muscles around the shoulder joint is still not known. So we're just scratching the surface. There's still a lot more that we can do with modeling to understand more of shoulder function and biomechanics.
And then given the approach that we use, right, how we made 1,000 iterations of a base model, I mean, you could do the same with rotator cuff deficiency, for example. You could have a population of different levels of rotator cuff deficiency and investigate, how that would affect the outputs of the model. Having, a population with varying degrees of rotator cuff deficiency.
Yeah. So I think we're nearing the end. Maybe we can take one or two questions. Like, one guy is asking, how did you simulate the interaction at the joint? But maybe I can just quickly answer that. I think you didn't really change that part, did you? The glenohumeral joint itself is still yes, just modeled as a spherical joint, right?
Yes.
Yeah,
that's correct.
But there are of course approaches where you could change the joint to be a contact kind of joint, but since that's not really the point here, you just want to know the overall force. I think a simple model like that is more than sufficient.
Exactly.
Yeah. Then finally, we have a question. Somebody's asking whether you have published this work.
Yes. If you guys are interested, you can find it. It's the title of the paper is Scapulothoracic Rhythm Affects Glenohumeral Joint Force, and it was published in JSES, the Journal of Shoulder and Elbow.
I promise that everyone who's listening here, they will get the citation in the follow-up email that will come out in a few days. So all of you will definitely get these links to the relevant part, and also we will be sending out the presentation here as a YouTube video to everyone who attended and signed up. So you can hear it again if you want. But then finally, Daryl and Cesar, I want to say thanks a lot for participating here in the webcast and letting everyone know what you're working on. That was really nice and really interesting.
All righty. Thank you, Morten.
No problem. And to everyone who attended, thanks very much for spending some time with us. I hope you will join us again some other time. So bye to all.
Okay.
Bye-bye.
Bye.
Good.